So we're down to here analyzing malicious Windows programs and the Windows API. Microsoft, if you want to control anything in the Microsoft operating system, like open a window or accept user input or send something out the network card, you aren't allowed to do that. You're not authorized to actually do anything if you're user land. Only kernel land can touch the devices and the device drivers, so you cannot just do anything you want. Which means, for example, a whole generation of hacking tools ended with Windows 2000. Because until Windows 2000, you could have raw sockets. You could have direct connection to the network card. You could send out packets bit by bit any way you want. And you can still do that on Linux, but you haven't been able to do that on Windows since Windows XP. And so a whole generation of fast scanners and hacking tools went away because they don't run on Windows anymore. But Microsoft is not interested in being a platform for hackers. They're interested in being a platform for business that makes money. And so they really don't care if you want to adjust the TCP timeout or send packets with a strange combination of flags, then go get Linux, because they're only here to help you do normal business things. So you have to use their libraries, and that's the API. And it's the same if you go to Facebook or Twitter. They have an API, so you can write a client that plays games on Facebook or something, and you can do a bunch of things, but you can only do things they want you to do by calling their API calls with whatever functions and parameters they let you have. So Microsoft has been, API has been around for a long time. There's been a lot of versions of everything. So there are different words for C data types. It's all ultimately written in C or C++, but they use D word for 32-bit integers and word for 16-bit integers. And they have this thing called Hungarian notation, where they put a prefix before the name of the function to tell you what it's going to do. So if it starts with W, it's going to take a 16-bit unsigned value. DW is 32-bit. If it starts with H, it's a handle referring to an object, and I think this is what it's going to return. Oh, variables. Variables are named this way. And then long pointer is a pointer that points to some other type of object. So those are common ones you'll see. Handles, everything you do in Windows, every named object has a handle. Every open file that you're using and other things. So Windows, processes, menus. If you open a window, you get a handle to the window, and then you close the window or resize it or something by calling something with that window handle. This is a standard way C does everything, although in C, those things are often pointers. In Windows, they are a more complicated, more abstract object called a handle. But anyway, all right. So you cannot do math on a handle. You can't assume they're sequential. You can just refer to the same handle later to refer to the same object. That's the only thing you can do with it. So create window EX returns a handle to the window, and then when you want to destroy it, you destroy it with that, which is the same way you handle files in C. All right, you can create a file, read a file, write a file. You can create a file mapping and map view of file, and that will load a file into RAM. And that's a way to run a program without using the Windows loader. Now, this is a very powerful technique for malware. In the work file in Python, I learned how to do this very easily in Python, where you read a file as data, you copy the data to RAM, then you just jump to it and start executing it. You can do that. It's not the official way to launch a program, and if you do it, it totally fools the antivirus utilities. The guy wrote the book like 4 years ago, and he was amazed when I told him it still fools all the antivirus. They don't understand what's going on at all, and they don't flag it even when you put obvious things in there that they should detect. So this is the whole point of malware is they will find some way to do important operations, like load a program and run it, in a non-usual way, so the antivirus won't catch them. There are special files out there. If you want to go to a shared folder on another machine on your network, it's / server name, then share name, or you can use this question mark in the middle of it, and that allows you to have longer file names. One thing that is very strange about Windows is that it still uses DOS 8.3 file names, and there are some hilarious command line tricks that rely on this. The longer file name is just an illusion. And if you do like a copy and replace on a group of files with stars in it, you're actually referring to the 8.3 file name, and there are some hilarious disasters caused by this. Anyway, so backslash is the lowest namespace at the heart of everything, like slash in Linux. Backslash dot backslash then takes you to the device namespace, so you can do direct input output. And so there was a worm that wrote to this thing, // physical disk 1. That will be direct output to the disk. You can do the same thing in Linux. by just /dev/SDA, but if you write directly to the disk, you write right on top of things like the partition table, just all important things, the master boot record, so you pretty much destroy the disk by writing directly to it, and that's what this malware wanted to do. This is quite a popular thing for APT type malware. The United States malware that we used with the Israelis against Iran had several versions, and it would almost always wipe out the disk afterwards to destroy all evidence. There's one called Eraser, one called Shamoon, there were a bunch of others. And the only reason they ever caught them is they failed sometimes and failed to erase the disk, so you were able to get a sample. Yeah.
But in this case, like, what are APIs things? Like you said,
these are not API calls. These are just internal Windows features. So you can write a program that writes to these objects. It's a good question what API you call. I think you just pass this as a file name into an API call.
Yeah, then you could just.
Yeah, and then it'll let you refer to these types. So they do support this in the API with these special file names. It's a good point.
Yeah, they only come as folders, so you can just open them like
Yeah.
files.
Yeah. All right, another kind of file is alternate data streams. This was a good way for malware to hide things until maybe 8 years ago. I think everyone's pretty much onto it now. This is one of those very few things you'll find in Windows that was added to Windows for compatibility with Apple. But Apple Music would come with alternate data streams. You'd have the name of a song, and you'd have the bits that made the music, and then you have the cover art, and the liner notes, and the copyright notes. You have multiple streams of data coming from the same file name. So the file name is like a folder and has many objects inside it. And that's how this goes. So you can make a file name foo, and then you can echo more data into foo : barred up text. Treat that file name as if it was a drive name and put a colon in it. And now you'll see that it'll tell you that foo still only has 4 bytes in it, but it's lying. The only thing that the DIR tells you about the size is the primary data stream. The alternate data stream is bigger, and you can now open it like notepad foo : bar, and there it is. So it is a curious thing, and until about Windows XP or Windows Vista, the command line utilities didn't see these things, and some antiviruses would not see things hidden in alternate data streams. I think everybody's pretty wise to it now. All right, then there's the registry, which is very important for anything to do with Windows. The original point of this was to clean up the operating system, because Linux is entirely different. If you install, say, Ubuntu Linux, and then you put something on it like Apache Server, it comes with a bunch of configuration files, and they have their own format and their own name and their own default folders, and every single piece of software has a different format, folder, place to put all those files, and you just have to study them separately. And that's, and Microsoft didn't like that, so they put everything in the registry. All the configuration settings for Windows and all the configuration settings for all the installed software, and this is why on Linux you can often just run something, but on Windows you have to install it, which makes the registry changes so that it can be found and put on the start program menu and such. Anyway, the main thing malware wants in the registry is persistence. There are many, many ways to make things start by putting keys in the registry, and they are called the auto start extensibility points. And unfortunately, like almost everything in Windows, there are just dozens and dozens of ways to do the same thing. So it is very hard to do a search and list all the things that automatically start when your machine starts. Anyway, the registry looks like this. There are 5 root keys: HKey classes root, HKey current user, HKey local machine, HKey users, and HKey current config. And these things are very far from what they look like. It's not one location with 5 folders in it. It's not even 5 files anywhere. It's actually stored in 13 files, not mapped one-to-one. The local machine is actually created during boot up by detecting the hardware. It's not stored anywhere on the hard disk. So if you add more RAM, and boot up again, local machine will change. And HKey current user is a subset of HKey users, referring to the currently logged in user and so on. It's a very strange structure, not simple at all. But that's the way everything is stored in Windows. And so you get used to these things. They're called root keys. Subkeys are the folders in there, and every key has to contain a value. If you don't put a value in there, it will have default value not set, which is another clue that these things are not like folders with files in them at all, really. It just looks a little like that in the tool. It's more like a database with a record, and you can't have a record that's just got, you have to have at least one record, or you don't have a container. Anyway, regedit is the tool you use to edit these things. Microsoft in one version actually made something called RegEDT32, which could read but not write, and it was a complete flop, and they just threw it away and went back to regedit. But one thing about regedit is if you go in here and change things, it takes immediate effect. This is like opening the hood of a car while it's running and going in with wrenches and wire cutters and changing things. There's no undo, there's no save. Anything you change here takes immediate effect. There are a few things you change here that aren't used until the next boot up, but most of them take immediate effect. So you can totally wreck your machine messing around in here. It's considered a good idea to back things up first. All right, so those are the root keys. So HKey local machine has settings that are global to the local machine, which sounds insane, but what this means is they are settings that do not depend on who logs in. That's what's global about them, but therefore only affect the local machine. The current user are the settings that specify the current user, and that only takes effect after somebody logs in. Classes root is where it defines the programs mapped to the 3-letter file extensions and other things like that. And current config is the current hardware configuration. This is, you may remember, back in Windows 98, there was a recovery feature called boot to last known good configuration, and it's still in there. Now there are much better tools now, like System Restore, but before there was any of that, there was last known good configuration, and what that does is back up this one key. HKey current config is backed up. And so if you change something like a display driver, and now you can't see anything, you can go to safe mode, boot up to special mode with F8 and use last known good config, and it will use the backup of this to use your previous set of drivers. So that's what it's not really much use for fixing a broken machine anymore, but it is actually useful in computer forensics because it means there is an extra backup copy of that registry hive, which might contain things that the perp tried to hide, like plugged in USB sticks and stuff. And then there's HKey users, which defines the settings for all the users, and when you log in, one of them gets moved, gets copied or linked to HKey current user. But anyway, for us in malware analysis, our primary interest here is not configuring things like the background and stuff, but getting things to automatically start on boot up, because otherwise, when they restart the machine, your malware will be gone. So the run key is over here, HKey local machine software, Microsoft Windows current version run, and this is one of the more simple, obvious places to put something. And you'll see I got various things here, Soundman, some kind of sound manager runs, log me in, Dropbox runs, and so on. Various pieces of installed software have chosen to put a item in the run key, and all it has to have is a path to something to launch every time the machine boots up. Sysinternals from Mark Rusinovich is the best tool for this. He's a fantastic guy. He had a great company, and Microsoft just absorbed the whole company, and now he's a big shot at Microsoft running Azure and other things. And this is the best tool I know to find everything that starts when Windows runs, and it is, of course, not perfect. There is no force on earth that can find everything that starts when Windows boots up. But this is about as close as you get to it. So DLLs loaded into IE, drivers loaded into the kernel, 25 to 30 registry locations, all the things he can find. Has a long list here, and these are all the things that will start when Windows loads up. And you can see everything, or you can see various categories up there, like network providers, services, and so on. So when you have a machine, say with malware, and you're trying to clean off the malware, understand it, this is one place you could go to get a pretty complete list of all the things that are automatically starting. I don't think people have this problem as much as they did back in the days of Windows 98. Back then it was very common that if you used your machine, you'd get too many things starting and it would take forever to boot up. It was hard to find them and stop them. Nowadays that doesn't seem to be quite so common. Anyway, so the registry functions that your malware uses to make those keys, these are the API calls, they're just what you figure they are, reg open key, reg set value, reg get value. The EX at the end, it means it's extended. So there was an earlier version in some earlier version of Windows, and this is now the extended version of the function. You see that frequently. You even see XX sometimes. All right, and documentation for these things will often omit the trailing character, like W or A, in something like reg open key XW. They will just have documentation for reg open key X, and there will be a couple versions of it out there. So it's a thing to be aware of. So here's these suffixes. You'll see things like create window X, and sometimes you'll have two X's, then you'll have an A or a W, which won't appear in the documentation. So you get used to the way these things look. It's a real good idea to understand the pattern for Microsoft functions like create directory W or create directory XW, because if you run strings on malware, you get just this name and nothing else. And if you can recognize that that looks like an API call, then you know what you've got. It's not something else like some scrap of documentation spelled wrong. All right, so here's the code that modifies registry settings in assembler. And it's been, they've disassembled it in a product like IDAPRO that lets us at least see the name of the function. So like I say, whenever you're faced with assembler and you're not good at assembler, start over on the right and look for things you can recognize, like value name, reg set value EXW. Well, that sets some registry value. There's reg open key EXW. So it's pretty obvious what this does. It goes to, there you have a string, software Microsoft Windows current version run. So it opens that key with reg open key, and then it puts something in there. And somewhere in this mess, it's calculating the path to put in there, which is not obvious. That's probably this here data plus stuff. But anyway, you can have a pretty good idea what's going on here. This stores a registry key. And so you can either dig more into this static analysis, or you could run dynamic analysis and use RegShot, which will show you what registry keys are created, and be an easy way to find out what's going on here. But anyway, that's a start. You can also make reg files. I don't know how much malware does it. They might. Malware tends to use simple tricks like this. You can go into Registry Editor and you can save a key. And you can save it in various formats. But if you save it as a reg file, it's just a plain text file. And when someone runs that file, it changes the registry. It's a common way to store registry hacks. You save it as a reg file, like run key reg file. And it looks like this. It's actually easy to read. In text, it just has comment at the top, and then it just has, in a certain format, the path, the name of this thing equals that. And then minus n VM user and so on. So it's just got these simple commands that are easily readable. So one thing, if you want to set registry keys, one way you could do it would be to download a file from the web and run it to set registry keys, if you don't want to write your own API calls. All right, so I got a few of these iClicker questions. Grab one if you need one. All right. Yes, okay, there we go. Let's put this thing, I remember up here seems to be the best place. All right. All right, so which prefix indicates a 16-bit value? Something wrong with that one?
Position is 68, but it says 69.
Oh, okay. I'll just move the, okay. Yeah, people put them back in the wrong place sometimes. All right, good. All right, well, I'll quit it a minute here. All right, that Microsoft calls 16 bits a word, which is kind of a funny thing to call it, but anyway, that's the way they do it. All right. All right, which prefix indicates a handle? All right, so I got quit at 20 on this one. All right, that's of course H. Good. All right. Which one lets you have longer file names? All right, I'll quit at 25. All right, that's the one with the question mark in there. Good, the most popular answer. All right. All right, which one lets you have direct disk I/O? I'll quit at 25. All right, and that's the one with the dot in the middle. Good, popular answers. All right. which one indicates function has been revised? All right, I'm quitting at 25. All right, that's the one with the X on the end for extended. Good. All right. Stop that. All right. Which one indicates that it uses Unicode strings? I'll quit at 25. All right, that's W, A is ASCII, and W is what they call wide letters, Unicode, for international languages. This got me around Christmas when I was doing another 100 Android apps. There were Android apps that stored your password in plain text, but in Unicode. And you can't find them with grep. You have to do like 4 Unix commands piped together to turn Unicode back into ASCII and then find it. So they may have slipped a few of those past me before I learned how to do that. Anyway. And that you find the people that actually want to make international apps, they put it in Unicode. All right, so the networking APIs. There's a few choices, and of course, this is the same thing in Python. There's an easy one and convenient, and there's another one that's harder to use that's used more by hackers and such. Yeah?
I had a question on the quiz.
Yeah.
And I put that right there and it said it was wrong.
Well, okay, I've got to check into it. Send me an email so I can.
did.
Okay, I'll check it after class. Thank you for telling me. If they're a bad question, I can actually regrade, it'll automatically regrade everybody. So let me know. I'm writing those things and there are mistakes in them, so help me find them.
The answer said it was way behind that or something.
It was enhanced networking was the, you said was the correct one, something about the
Enhanced networking.
yeah, the option was something like enhanced networking versus the standard.
All right, well, I'll have to take, something wrong with the networking question you said, okay?
Yes.
All right, well, here's the WinSock. You may remember a site called 2 Cows, the ultimate collection of WinSock software. These things use standard networking. Remember, Microsoft started without any internet. The original theory was MS-DOS and you have your own printer. Then they reluctantly extended to NetBIOS so you could all share a laser printer in the room, and that was all they thought made any sense. They thought the internet was a total waste of time and completely ignored it until AOL came out. And then Microsoft realized they had really missed the boat and they rushed with Windows 98 into drastically grabbing at the internet. But anyway, the point is the internet was a Unix production, and Microsoft didn't come in until really late. So the first thing they could do was just copy the standard Unix functions to get to the internet, and that's what this is. These are Berkeley compatible sockets from BSD Unix.
Yeah, so the answer was WinNet.
WinNet DLL.
WinNet DLL was chosen as the correct answer.
Okay, well, I hope it's in an email. I can look at it offline.
I have it in the book.
All right, well, if it's in an email, then I'll find it.
Yeah.
Okay. All right, so socket creates a socket, which you do before you can connect, then bind attaches to a port so you can listen, or you can connect, which opens a connection to a remote server. And you receive and send with RECD and send, and this is how we do everything in Python, in the Violent Python class, and it's very much the same in Windows. However, first you have to call the WSA startup function before you do anything else in Windows to prepare the structures that are needed for these things to work. So you might want to watch for WSA startup, and if you put a breakpoint on WSA startup in a debugger, then it will stop right before it makes a network call. And that might be a good place to stop if you've looked at the networking traffic with dynamic analysis and decided that something interesting happens around the time of a network call. That sort of thing would have helped me because I was struggling. It took me a day and a half to break into the latest Citibank Android app because they changed the way they handle passwords, and I was struggling hard to catch the code right before they went to the network. So I could try to find where in the world did they hide the password. Anyway, so the server side, you call socket to create a socket object so you can do any networking. And then you call bind to bind to a port, and then you call listen to listen on that port. And then you accept data, so that's what you'll have, and then send and receive. On the client side, you call socket and connect, and then send and receive. So you can tell the server side from the client side in assembly language by looking at the order of the calls. Only the server listens, and only the client connects. All right, so here's a simplified server program. First you have to call WSA startup, then you call socket, bind, and listen. Now you're ready to receive data, so you accept data. That's a very simple one. Of course, realistic servers send and accept over and over. Receive from data, give you an answer, receive from data, give you an answer. All right. And by the way, code that actually handles errors would keep on calling WSA get last error, because professional code doesn't crash all the time. Every time you try to bind to a socket, it checks to see if that failed because maybe something else is listing on the socket, then it handles the error. But if hacking code usually doesn't, like shellcode. It's written to be small, and you're an attacker, so you really don't care about making it professional, so you skip all the fancy stuff. And you accept the fact that your code will just die with no useful error message if anything goes wrong even a little bit. This is true of Metasploit shellcode. If you make shellcode with MMSF Venom and your networking is down, it will just crash when it tries to make a network connection. It will just freak out and die on you. It takes a little getting used to. So the WinINet API is the higher level one that a normal programmer would use. And here you get functions that do a lot more, like internet open URL, internet read file. This will just download a file from a location. This is like using a browser, much more convenient, and what a normal developer would use. Going down to the Berkeley sockets is something a normal developer would not waste their time doing. You just, well, want to do these sort of things like HTTP and FTP, why bother doing it packet by packet down at the bottom? All right, got a few more of these things. All right. All right, so which function will be called first when you're making a network connection? All right, looks like I can quit at 25. All right, you got to call startup before you do anything else. All right, good. All right, when you're starting a server, which one will we call first? All right, I'll quit at 25. Well, you have to call startup, but it's not on that list, so the one on that list that's called first is socket. First you make a socket, then you bind, then you listen, then you accept. All right. Making a socket just creates a handle you can use for later operations. All right, when you start a client, which one of these will be called first? I'll quit at 25. All right, same thing. You have to start by creating a socket. Then you don't bind, then you connect. And then you send and receive. You don't bother binding and listening. All right. And which API uses commands that are very similar to those in Linux? Quit at 25. All right, that's WinSock, glorious WinSock. All right, they're not both the same. WinSock is the one that follows the Berkeley standard Linux protocol, Unix protocol. All right, so you're running malware. Is going to, you can use jump and call to call a subroutine and to move somewhere else. But there are many other ways to cause malware to stop, to cause a program to stop what it's doing and go run some other code, and all these are possible ways for malware to get in. One of the most common ways is DIL injection. You add a library, and as soon as you load a DIL, it has to run a DIL main to initialize the library. So it stops whatever it's doing and runs DIL main, and you just put your malware right there. So it's one way to get in. And you can do any of these other objects can be used to to have an effect on execution, although I don't think a mutex can have one directly. But services certainly can. You can make your malicious malware can be a service, and then you call the service, and you can use the component object model to do it also, and exceptions, and so on, like we've said. So DLLs. The purpose of DLLs is to have a library that's shared among many applications and exports a lot of entry points. And now in the past, they used static libraries, which are still common in Linux, where you would have, if you loaded a library like WinINet, you would add it to your program, and if WinINet was 50 megabytes, I don't know how big it is, your program would now be bigger by 50 megabytes. And if 5 programs are running that use WinINet, you'd have 5 copies of WinINet in RAM, hogging up RAM. This wastes a lot of memory, and it makes it bigger on the disk, and it's slower to load, but it also means they're completely independent. If one of them gets hacked or crashes, it doesn't affect any of the others. But Microsoft Windows always uses the other technique. I'm not aware of any Windows software that doesn't need static library. I think in principle it's possible, but nobody bothers because dynamic libraries are so much better, most of the time, where everybody's unsanitarily sharing the same DIL file among many processes. So that's the idea. It makes code smaller, it makes it load faster. It means you can run more programs at the same time, at the same amount of RAM. And you could also now manufacture DLLs and sell them, and people will just buy them. And that's the Microsoft way. You can now make money selling software, which is the point of the thing. The purpose of Facebook is to make money selling software and games and stuff too. They're platforms that sit there, and the only reason people pay for Windows or Facebook is because of people that put apps on them that do fun things. So, all right. So you can, your malware author, of course, puts malicious code in DLLs, and you may load that DLL into another process, or they can use Windows DLLs. They almost all do use normal API calls to do things like create files and modify the registry. You can also use third-party DLLs. This is a trick some people do. They take a third-party app that almost everybody has, like Firefox, and use its DLLs just again to evade antivirus and confuse malware analysts, because you won't see any calls to the standard Windows libraries to do things. You'll be using the Firefox libraries, which will still infect almost anybody, but you might not get caught. This is one of the reasons why iOS is so secure, because there is not any third-party code that's installed on basically every iPhone. Whereas on Windows, certainly until recently, everybody had Flash and Java, and now pretty much everybody has Chrome, and a lot of them have Firefox, and so you can assume that that's there without cutting your infectable target list too much. It's rather interesting. One was a news article earlier today. The FBI found pedophiles by infecting a Tor hidden service. They did exactly what Anonymous had done a year earlier. They hacked into a Tor server without finding where it was. They replaced the home page with a home page that said you have to update your Tor browser bundle, because all the pedophiles and other criminals use the Tor Vidalia bundle, where you install this thing and automatically routes your traffic through Tor, and that thing is an old version of Firefox because they don't update it very much. So they found an attack, a 0-day, to go into the old version of Firefox and used it to infect those machines. And they just decided to let one of the pedophiles go, because the court proceedings said you had to reveal the tool you used to get this evidence. You can't just tell us you run some magic tool and it found his evidence. We have to be able to see the tool, and then it will go in the court records and that will expose the tool. And they decided that protecting the 0-day was more important than punishing the guy. This is a big issue these days. The NSA does things that the FBI is not allowed to do, to find data. Then they leak the data to the FBI. Now they know who did it, but they can't use that evidence in court. So they have to try to run around and find some other evidence. It's all very strange and close to being illegal. Anyway, like most things. All right, so a DIL looks like an exe. It's a PE format. There's a single flag that says it's a DIL, and it has more exports and fewer imports. So DIL main, like I say, DIL main is the original entry point. This is what is the analogous to main in a normal program. And as soon as a DIL is loaded, it calls DIL main, or when it unloads. DIL main is what sets up the DIL, prepares it for use, and tears it down to free up all the objects when it's no longer in use. All right, every program has a process, and every process has handles in memory and threads. The threads are the allocation units of computer time, because the threads can move forward independently. Back in the old days, when you had a single processing machine, like MS-DOS, I remember this, you would make your letter in Microsoft Word, and then you would hit print, and then you would go get coffee, because it would take 5 minutes to print, and you could not do anything else while it was printing, because it could only be doing one thing at a time. So if it was printing, you couldn't do anything. And multi-threading is the modern solution to this. You have multiple processes running at once, and each of them is broken into threads, and every thread can move forward one by one. So if any one thread is waiting for something slow, like the printer, other threads can move. So as we know now, you can be downloading a file, you just open another browser tab and do something else, and the download continues through the miracle of multi-threading. So anyway, older malware ran as an independent process. The sneakier stuff hides as an existing process. And if you use Metasploit, you get used to this. You take over a machine and then you migrate into another process. Because if you take over a machine, say through a browser exploit, you end up running inside the browser process. And that's not good because you're probably fouling things up and the user's going to close the browser pretty soon. So you migrate over to something else like Explorer.exe, which is the process that draws the desktop, which lasts until they log out. And it's a better place to hide your malicious activities. So here's all the processes running on a Windows machine. Here's the famous Explorer.exe, which is the one that starts as soon as you log in and continues until you log out. And here's all these other things that might be running, like Adobe ARM and so on. Well, I don't know if anybody's still using that. Anyway, so all right, so each process uses resources. And if you have two processes accessing the same memory address, they're actually accessing different locations in RAM. Each process runs in a sort of virtual machine. It's not as separated as a virtual machine, but it runs in a virtual address space. Every exe thinks it's running at the same memory location, 400,000 in hex. They're rebased and they don't know that, or they're moved to another location. DLLs load at various different places preferentially, but they can be moved to another location. If they try to load in their preferred memory and that's full, they'll move to another memory location. And that's their virtual address space. So if you want to create a new process, which is how almost all the Metasploit attacks work, you can watch them go. Remember you were doing an exploit development class. One was I think a heap overflow, and they're creating a new process. And so the original process terminates, and a new process appears listening on 4444. This is one of the more common tricks you do. So you do it with the CreateProcess API call. And you now have a parameter that contains all this information for the inputs and outputs and such. You can also set it to a socket, and then the new process will be listening on the network, and that is typically what you want to do to make a listening shell. Of course, listening shells are not the most powerful attack. What's much better is reverse shells that phone home. If you just listen, then if they have a firewall, you won't do any good because you listen on some unexpected port, and they're blocking all unexpected ports. So it's available though. Better thing, which you also do by creating a new process, is phone home as a client, not a server, saying, please tell me what to do, because that will go through the Windows firewall. So here's code to create a shell. You call it, so it's going to load a socket handle. And then what it's going to do here is, see, it's just doing one call. It's getting a bunch of stuff, push ECX, push EDX, move, all this junk. And these moves are going ESP plus places, so these are actually like push. These are putting it on the stack. So you're just loading a whole bunch of parameters on the stack. And the parameters are the socket handle, and then standard error output, handles to standard error, standard output, and standard input. And up there, that junk up there, that's the socket handle. ESP plus 58 plus socket handle, way up in the first thing. So you just put all the parameters in the stack, and then you're going to call the API call. I think there might be more of this on the next page. Yeah. So when you're done, you call CreateProcess. So this is what a function call looks like. It's just a complicated function, so it's about 20 lines of assembly. But you're just loading all the attributes in reverse order and then call. You create a process. So a process is a container, and the container actually contains a bunch of threads, which are the individual blocks of code that can move forward. All right. These are independent sequences of instructions that can move forward without another thread being required. And threads within a process share the same memory space. They have their own registers and stack, but they share the same RAM. They can see each other's data. So this is called a thread context, and it is called a context switch when the CPU moves from one thread to another thread, which is internally different than, say, a function call, where you store everything and make another stack frame. But it's a similar system where you have to somehow save where you left off and go do this for a while, and then later on come back. And the processor has a sharing routine that is choosing how many cycles to give each thread as it strobes across them, just like a server cluster where you have requests coming in. It decides which server to give the request to, either based on just round robin where it takes turns, or some more complicated algorithm that tries to give it to the least busy server. So that's the change. So a thread changes the register. It doesn't affect any other threads because they've saved the registers when they quit having CPU cycles so they can pick up where they left off. Anyway, but when it switches to another thread, it saves this in a data structure called a thread context, which is the analog of the stack frame, which is what we've seen where you have a function and you call a subroutine. So create thread creates a thread. You specify a start address, and you load a malicious DIL into a process is one simple thing you can do. Create 2 threads for input and output. Then you can send input to an application and take output from the application, something like a browser. And then you got the all-important question, how do you know if this machine is already infected? Somebody gets another copy of the same malware and another email, they click on it, you might end up infecting the same machine many times. And various malware authors have made this mistake, where machines get infected many times until they start freezing and crashing and you get caught. So mutexes are global objects which are handles shared across threads and across processes. So you can create a mutex with a special name, and then you can check for that mutex before you infect the box, because if that mutex is in RAM, that means another copy of the same malware is already running. That's why, I probably told you this, someone told me on Twitter about a week ago that at a conference they said, there is a way to protect, I think it was this visiting speaker last Monday, he said there's a way to protect your machine from ransomware by running code that will create mutexes for all the known ransomware. So it thinks you're already infected with everything. And that sounds awesome, but I've not been able to find that tool or papers about it or anything. If somebody finds it, let me know. That sounds great. Anyway, that's like the original vaccine, right? You give you a little bit of weak smallpox, now you don't get the real smallpox. Anyway, so it sounds good. All right, so here's functions. You can wait for single object. This will give a thread access to the mutex, and any subsequent processes will have to wait. That's why there's another use for this mutex besides for malware. You might be using something that only one process can use. For example, you're printing a document, and then somebody else wants to print a document. Well, you don't want half of their document and half of my document. I want to have sole possession of the printer until I'm done and let go, and then one of the other processes waiting will get sole possession until it's its turn. So frequently, that's what these things are for, resource locking, so you know who's using it. Anyway, so these things like wait for single object, release mutex, create mutex, and open mutex are the calls you'll see to manipulate these mutexes because 2 processes are sharing some resource and they have to make sure to control who's using it. All right, so here's the code that makes sure only one copy of malware is running. Let me try to find yet another place to put this thing. All right. So it calls open mutex, and then down here it calls, it gets mutex after it and calls create mutex. So what it does, it checks to see if it exists. It opens mutex and then tests EAX. This test right here will be 0 if EAX is 0. That's what it does. Not obvious to me at all, but this will tell you if EAX is 0. So if it's 0, forget all this and go down here. If it's not, then exit. So 0 means it did not find that mutex. It was able to create that mutex. There was no error. So since it was able to open the mutex, if it had, let me try and get this right. Here's my understanding. If it opens the mutex, it will get a handle to the mutex. Or something, some non-zero result. If it gets 0, that means, well, anyway, I'm not going to struggle with it. You have to read the documentation. The point is it tests it. It looks to me like 0 means that the mutex is available and you can infect this machine. Create the mutex. Non-zero means the machine is already infected. So that doesn't make sense. Non-zero means you've got some response like a handle to it, and therefore forget this and just call some exit. Do not infect the box. So, you know, if I'd run that magic tool, I would always go this way, and it wouldn't bother infecting me, which would be cool. Anyway. So services run in the background. You can see them in Task Manager on the Services tab. These are programs that do not directly do anything for the user. They provide services in the background and are called by other processes. So you've got things like BitLocker Drive Encryption Service, which a computer browser. Computer browser is what sends out packets on the local area network to find out what shares and printers are on the local network and keep a map of them, which used to be called Network Neighborhood and I think is now just called Network. But these services are running in the background doing things like that and are called by various processes as needed. However, many of these services run before you log in. And in order to do that, they have to run with system because you haven't logged in yet. They can't run with your privileges. They can't even run with the administrator privileges because the administrator hasn't logged in yet. So they run with system. System is the account designed to run things before people log in. It is more powerful than administrator to have system, and you'll see this if you play with Metasploit. If you want to do things like dump password hashes, you have to elevate all the way up to system. It's not enough to be administrator. So that's the game. So if you can register your malware as a service and set it to automatically start, that's an easy way to get persistence. And it will often run as system. So it'll have all the power you want and it'll automatically restart all the time. You can control these things from the API with SC Manager. So you open SC Manager to get the Service Control Manager, and then you can create service, start service, and so on. And you can have parameters that tell it to automatically start at boot time, and so on. All right, then there's SVC host. This is the most common type of service. Win32 share process. There are different kinds of services, but if you run a share process, it'll run as an SVC host.exe. You'll see these things in Windows. Let me just bring it up here. Yeah, you may already know this, but Windows 10 will be fine. Let's look at Task Manager and running Windows 10. All right. And I don't care about that. Quit would be good. All right. So, Task Manager. Whoa, baby. Whoa. Okay, that's good. It's getting a little more readable as it starts various layers of junk. And there's glorious Task Manager. I want more details. And then I want services. Okay, so in Task Manager, you just see all these services. And that it's not obvious what the exe is that runs them. But in fact, a bunch of them are all running from the same exe. Like a bunch of them run with SVC host, and a bunch of them, so let's get down here. Should be SVC host, but in this modern, I shouldn't have started this version of Windows. It makes everything unnecessarily confusing. Let me see if I have Process Explorer. I'm going to go back to, I'll do one try and then I'm going to go back to the other version of Windows. Yeah, I'm going to go back to the other version of Windows where I have the good stuff. You can do it on that version too, but it's easier to do here where I've got all my pieces. If you use Process Explorer, then you can see the EXEs that are running those things. And that should be here in, say, 126. Glorious Process Explorer, there we go. We've been using this thing. And now, here's SVC host, and there's all the things this instance of SVC host is doing. DCOM service launcher and plug and play, but there's another SVC host here running remote procedure calls, and another one here running a few more things, and so it goes. Each one of these executables is running several services, and the built-in Windows tools don't make it easy to untangle them, but Process Explorer does. Anyway, if you use this kind of process, it'll be one of the ones run by SVC host. All right, and there's another picture of the many SVC hosts running many things. All right, there's other kinds. Here's an EXE that runs in an independent process. You can actually have a service that is one and only one EXE. You can have kernel drivers, which are going to load code into the kernel and then run in ring 0, and that's where device drivers run. All right, so the services are in the registry. You can see a list of services here in this thing called HD Local Machine System Current Control Set Services. And then I went into the particular service called Browser, which I mentioned before. That's the one that scans your local area network to see what you've got. And here's various things you see over here. Start value is 3, which means it will load on demand. And type is 020, which is a Win32 share process that runs an SVC host. So that's what it looks like in the registry. The SC command is a command line command you can use to create these things and start them and stop them. And that command will then go make those registry entries, as will the Service Control Manager, the graphical one. All right. And here it just shows me the information about browser, and here's the same information in another form, start, type, and so on. All right, I've got a few more eye clickers, and then I think we'll take a break. Try and keep people awake. All right, which item replaced static libraries? All right, I'll quit at 25. Those are DLLs. Dynamic libraries are the alternative to static libraries. All right. Which one is used by malware to check if the malware is already running? Good, I'll quit at 20. All right, that's the mutexes. If they were in the kernel, they would be called mutants, but they're not in the kernel typically. All right. Which one contains one or more threads? All right. I'm quitting at 25. All right, a process contains one or more threads. I was just sitting here wondering if some of the other answers have some truth in them. But services might not be running, and this might be on the hard drive. Anyway, process is, I think, the best answer. I was wondering if picky people might find some truth in the other answers. All right. Where do you go to have more power than the administrator? All right, I'll quit at 25. All right, and you go to services because they're often running as system. All right, so it's 7, let's take a break till 7:10, and then we'll finish this up. And it's 126, chapter 7A.